Hey everybody, hello from Maryland. I'm just going to do a brief lecture here on digital filtering that I hope will put together a few pieces that we've been talking about lately. Hoping you guys can watch this lecture between now and Tuesday, and I can talk about it when I'm back on Tuesday. All right, so we've been talking about discrete time systems a little bit, and we've been talking about signals and noise a little bit. So I thought it might be really useful to give you one of the most practical tools that I can as far as improving the signal to noise ratio of a signal, and that's the ability to generate your own digital filters or discrete time filters. So we talked about discrete time systems where you have an input x of n, you have an output y of n, and then your output is some combination of your inputs, delayed and scaled, and your previous outputs, also delayed and scaled. We talked about how different values on the scaling factors here can actually give you different frequency responses and different effects on the input signal, and that you would calculate the output by convolving the impulse response of this discrete time system with the input. So we looked at how the impulse response can be found. If it's a system with no feedback, then the impulse response is very simple. It's just the feed forward coefficients. But if it's a system with feedback, then we haven't looked at how to find the impulse response. We've just let MATLAB do that for us. But anyway, we can find the impulse response. And then to predict the output for any given discrete time system, we simply convolve the input with this, the impulse response that we found here. All right, so we talked about that in lecture, and then you guys did that in lab 6 a couple weeks ago. So that's discrete time systems. And we looked at how, depending on your impulse response, so here's your impulse response here, depending on your impulse response, you may have effectively low pass filter, high pass filter, band pass filter. For this particular example, when we did this in lab 6, it ended up that this was a low pass filter. And the output, the filtered output, YNF, was equal to simply the convolution of xn and yn. Right, so xn, sorry, I should go back. Convolution of xn and hn. So as xn goes through a system, h of n, then you get y of n at the output, which is simply equal to x of n convolved with h of n. Okay, hopefully so far so good. That's stuff we've talked about before. So we've kind of shown that different h of n's can represent different kinds of filters, low pass filter, high pass filter, what have you. But we haven't really talked with any seriousness about, well, how would you choose the coefficients for yourself? And so that's what I wanted to talk about today is, so what if you wanted to design your own digital filter? It's a discrete time system, and you want to make it so that by choosing certain b values, that is the coefficients that weight the inputs, and certain a values, that is the coefficients that weight the previous outputs, you can choose what filter behavior you're going to get. This is really practical, it's really common, and thanks to MATLAB and other filter design toolboxes, it's actually really easy to do. So I think this is a nice quick practical skill you guys can pick up. So let's do a couple motivating example cases here. And these are based on some of the signal and noise plots we made the other day. So let's say that we wanted to filter out noise for I'm going to call it a baseband signal. So here's a signal on the left. It's a pulse, a short rectangular pulse. Here's our signal in time. Let's call it x of t. And we have our signal blue, and then noise is added to it, orange. The signal to noise ratio is 4, so the noise is relatively strong relative to the signal. And when we add those up, then we get a noisy pulse. Okay. In the frequency domain, we have the signal in the frequency domain, and it has content at low frequencies starting down at DC. The term for that is baseband, which means frequencies from 0 up to, I'll call it some cutoff frequency, FC, after which there's no more energy in the signal. So in the frequency domain with the signal plus the noise combined, you can see that the signal contributes kind of all the way up to 10 kilohertz, and then after 10 kilohertz, you're basically just looking at noise, right? So we would say this is a baseband signal whose bandwidth or cutoff frequency would be about 10 kilohertz, right? So if we wanted to remove some noise from this signal, we can't filter out the frequencies where the signal lives, but we can filter out all the other frequencies, remember? So the question is, what if we wanted to make a digital signal that would remove all the frequencies above 10 kilohertz? That would improve the signal-to-noise ratio. Our second motivating case is, let's say we have a sinusoid and we add noise to that sinusoid. So over here on the left, the blue sinusoid, and then you've got the orange noise. And then when you add them together, you have the signal plus the noise, SNR equals 4. And so, of course, you can see they're a noisy sinusoid. Well, what if we wanted to get rid of it? If we look in the frequency domain, we see that that signal is quite strong at 5 kilohertz. That's the frequency of the sinusoid. And the noise is really pretty weak, but it's everywhere. What if we could remove all the noise that's not around 5 kilohertz? So what I mean is, what if we had a bandpass filter whose gain curve looked something like this? Whose gain curve looks something like this, so that it would remove all the frequencies away from 5 kilohertz and just leave us with the frequencies near 5 kilohertz where the signal lives. That would remove a lot of noise. Okay, so those are our two motivating cases. And if we choose our coefficients right, we can make a bandpass filter for the one case and a low-pass filter for the other case, and thus improve our signal-to-noise ratio. Okay. Okay, there's two kinds of digital filters that I want you to be able to use. The first is called finite impulse response. I mentioned this in class when we were talking about discrete time systems, but a finite impulse response would be a filter system with no feedback at all. So you can see it's fully defined by its B coefficients. These are the easy ones that we looked at. And then the infinite impulse response is when there's feedback involved. You can see the feedback here as defined by the A coefficients. So these are more complicated, but they can be really powerful. Okay, so let's look at the finite impulse response first and think about how we can design our B coefficients so that we get whatever frequency response we want to improve the SNR. All right, so when we do finite impulse response, here's the design sequence. First, we're going to define our filter type. Do we want a low pass? Do we want a high pass? Do we want a band pass or a band stop? And then, depending on which type you have at least one cutoff frequency, maybe more. So you define those. Then you think about your sampling frequency. Maybe I don't care about my sampling frequency. I only care about my cutoff frequency. Yeah, but because it's a discrete time system, there will be a sampling frequency. This is like an intrinsic part of a discrete time system, is to have a sampling frequency involved. So you have to think about it. If you don't have one that you care about, make one up. But if you have a signal that you're trying to filter, then your sampling frequency of your filter should match the sampling frequency of your signal. So if you have an X of n, and it has a sampling frequency, then that's your filter for your sampling frequency, okay? All right, then you look and you say, what's my normalized cutoff frequency? So we're gonna use the variable capital omega for this. The normalized cutoff frequency is the cutoff frequency that your filter is going to see. Bear with me here. The omega c is simply going to be the cutoff frequency, the analog cutoff frequency, over fs over 2. This might make sense or it might not. Remember that in a Fourier transform, when we're looking at the Fourier transform is fully defined from 0 up to fs, but everything after fs over 2 is a copy. And then when we looked at sampling, everything over fs over 2 was aliased. So fs over 2 is a bit of a magic number there. I think I told you when we did sampling, this is the Nyquist rate. It's a bit of a magic number. Everything above fs over 2 is somehow invalid. So when we do our filter design, we're really only concerned with the frequencies between 0 and fs over 2. So our omega is going to be the ratio of fc over that fs over 2 upper limit. So everything's normalized to that upper limit, that Nyquist rate. Okay, once you've got your filter, normalized filter cutoff frequencies, then you can use your filter design tool to calculate the B coefficients. Why don't you need A coefficients? Because we have no A coefficients in an FIR filter, in a finite impulse response filter. Okay, so that's all there is to it. We're not going to do any by hand filter design. There's so many great tools out there. We're just going to use tools built into MATLAB to do the calculations for us. Okay, so here's how to do the filter design in MATLAB. This is a function called FIR1, and this is as simple as it gets to start with. Okay, so we're going to define our filter type. In this case, we want it to be a low frequency filter. We're going after this use case right here. We've got a baseband signal and we want a low pass frequency, a low pass filter that cuts off frequencies above 10K. So coming back to here, we want a low pass filter. We want the cutoff frequency to be 10K. We're going to set our sampling frequency to 100K. And I'm setting that because I'm going to try to filter those X of N's that we just looked at a minute ago, and they have sampling frequency of 100K. So I'm going to use the same sampling frequency. All right, my normalized cutoff frequency then is going to be FC over the Nyquist rate. And then we come to a little bit of a arbitrary number. N is the number of coefficients in your filter, or the number of B coefficients. Here, that means N. Here, that means N is going to be the number of delay and multiply branches that you have in this discrete time system. So it's not, there's no hard and fast rule as to what N should be. 50 is a good place to start. The higher you make N, the higher your filter performance can be, but the more delay your filter will impose. So 50 is a decent place to start. If you go lower than 50, you might not get the response you're looking for. You could try it. If you go higher than 50, you'll get significant delays. We'll see that in a second. All right, so then you simply say B is equal to generate B using this FIR1 command, where you tell the FIR1 command what order you want, what your cutoff frequencies are going to be, and then what type of filter you want. Okay, and then it'll give you the B coefficients. This is all documented in MATLAB help center. Here's the link for it, or you can use your own help browser. And as you can see, FIR1 is just one of many design tools that MATLAB has available for doing FIR filters. All right, so how do we know that this actually did what we wanted it to do? Well, let's use the freq function to visualize what this filter's frequency response will be and make sure that it's a low-pass filter with a cutoff frequency of 10 kilohertz. So we're going to set A is equal to 1. That's the same as saying we don't have any feedback in our system. And then we'll do freq of FA, and this is to view the frequency response. We're going to do FC, or freq of B, comma A. All right, here's the frequency response. What are we looking at here? This is frequency going from 0 up to Fs over 2, which is the same as omega equal to 1. Told you, nothing's quite straightforward in discrete time systems, but hopefully you get the gist here. So this is frequency on the x-axis, and then we're going to have our magnitude on the y-axis. Notice that by default, we're plotting our magnitude in terms of dB, and that's because we're going to have really small numbers on this this magnitude scale. You can think of the magnitude as the same as gain, if that helps. Okay, so how do we know the filter works? Well, it looks like things are okay because we have relatively high gain at low frequencies and then low gain as we go up. So it looks like a low pass filter. Let's be a little more specific about that. Our passband gain, this is the passband over here. Everything from here to where it starts to roll off, that's the passband. Our passband gain is 0 dB, so that means the gain is 1. Our stop band gain, everything over here, stop band. This passband. Our stop band gain is negative 70 dB. How big is that? That's 10 to the minus 7th. So signals that go through there are getting attenuated by a factor of 10 million times. That's a lot of attenuation. That's a very, very small gain. So that's good. That means signals up to 0.2 normalized frequency, omega equals 0.2, are being passed with very little loss, no loss, gain of 1. And then signals well above that are being cut off by 10 to the 7th times. Okay, so the confusing part here to me is the 0.2 on the x-axis, because that's not a number that I really recognize. Well, that's the normalized frequency though. When we did the design here, that's what the normalized frequency will be. See, that 10 kilohertz, that 10 kilohertz cutoff frequency is going to get divided by fs over 2, which is 50 kilohertz, and you're going to get 0.2 or 1/5. So that normalized there, that means a frequency of 10 kilohertz because the cutoff, or because the Nyquist rate is 50 kilohertz. All right. $50,000, that's the Nyquist. Okay, so that means that we actually do seem to have high gain at 0 up to 10 kilohertz and then low gain after 10 kilohertz. We'll really know the filter works if we actually use it to filter our signal and the SNR improves, right? So here's our signal on the left. It's shown in frequency. As we remember, it's noisy. As we remember, the signal goes up to 10 kilohertz, and then after that, it's just noise. So let's look at this noisy signal, XT noisy. That's the blue one we're looking at here. XT noisy, we'll instantiate this same filter, and then we'll filter it using this filter command. You could actually use convolution. And as long as you did convolution XT noisy with B, and then you did a little same here, and you multiplied by TS, then that would be exactly the same thing. But you can see the filter does make that kind of convenient. It hides some of that from you. You don't have to worry about it. But filter is just doing convolution, I promise. There's nothing else tricky going on behind the scenes. Okay, so we use this filter command to do our convolution, and then we look at what happens after the filter. So before filtering, we've got this noisy signal after 10 kilohertz. After filtering, look at that. All the stuff above 10 kilohertz is knocked out because, why? This is the stop band. And so it's being attenuated by 10 million times. In the pass band up here, not much is changing, and that's the way we want it because this is mostly signal between 0 and 10 kilohertz. I hope that makes sense. We're keeping our signal with the frequencies where our signal is, and we're cutting out the frequencies where we know our signal is not. All right, so let's look at the time domain and make sure that nothing went terribly wrong in the time domain. In the time domain, we see that before filtering, we have a pulse and then noise after the pulse. After filtering, we've got a pulse and then very little noise. But the pulse has changed shape and it's moved. So are we okay here? In the frequency domain, things looked great. But after filtering in the time domain, this looks weird. So the first thing is the shift. Because there's 50 delays associated with this filter, remember? There's going to be 50 of these delay blocks associated with the filter doesn't really start truly working until 50 samples later. So the whole thing is shifted over by 50 samples. So the peak that we see here is shifted by a certain amount of samples, and thus it shows up later in time. That's not bad as long as we know it's happening. So that's okay. The second thing is, notice that the shape has changed from a sharp pulse to a more rounded off, almost like a sync-like pulse. Well, that's also to be expected because if you want a really sharp pulse, you have to have a lot of frequencies, and the high frequencies make the sharp edges. But now we've gotten rid of a lot of the high frequencies, the stuff above 10 kilohertz, and so our edges can't be as sharp as they were before. So we have sacrificed a little bit. By removing everything above 10 kilohertz, we've sacrificed the sharp edges on our signal. Is that good? Well, it reduced the noise a lot. Our signal to noise ratio is much, much better than 4 now, as we can see in this graph here. Our signal to noise ratio is, I'm sorry I didn't calculate it, but it's probably more like that 20 or above that we know we're interested in. So it's working. It's doing what we asked it to do. The ramifications are we've delayed our signal and we've rounded off the edges. Okay, so I hope that helps visualize like what will happen with the FIR filter, how we design it, and what the graphs actually mean when you get the graphs at the output. Okay, so that brings us to infinite impulse response filters. Oops. Infinite impulse response filters. This is the same story again, so just buzz through this. Just like with finite impulse response, you define your type, you define your cutoff frequencies, and you have your sampling frequency set. Then you get your normalized cutoff frequencies. Now your filter design tool is going to give you both B for the feed forward and A for the feedback coefficients. Now you've got feedback coefficients. Okay, so in MATLAB, the Butterworth function, the Butterworth design tool is the easiest one to use. So here's how you could use that to do the same kind of low pass filter. Filter type low, cutoff frequency 10K, sampling 100K, normalized omega C is 0.2. And now your number of coefficients can actually be very low for IIR filters, even as low as 2. I've got 15 here as a place to start, but you can actually go pretty low with IIR filters. And then the command is just butter to generate a Butterworth filter. All right, filter seems to work. Butterworth filters make very smooth pass bands, long transitions, and then very deep stop bands. The pass band gain here is 0, in other words, 0 dB 1 times. There's a really long transition region here. You can see it's 0.3 on a normalized frequency scale, but there's no ripple at all in the stop band. Remember the FIR filter had ripple in the stop band? This was the FIR filter response. So now with the Butterworth, totally different. No ripple at all in the stop band, and the stop band gain is just gone. More than 150 dB stop band attenuation. So you're getting nothing in the stop band. Notice this nonlinear phase. Not to go through the details, but this means that there's going to be distortion on our signal. We'll see that in a second. So before filtering, we had noisy signal up to 10K and then noise after 10K. Now we've got just that signal up to 10K and then nothing whatsoever after 10K. Okay. But now, after filtering, our pulse is not only shifted like it was before, but now it's also ringing. Interesting. And it's non-symmetrical anymore. That's because of the nonlinear phase. I don't really want to go to the details right now, but that nonlinear phase induces distortion of shape. So that's what we're seeing here with the pulse and the oscillation. All right, there's one other IIR filter technique that I think is worth you knowing because it behaves a little bit differently than the Butterworth, and you can, depending on what is important to you in any given design, you might want to use one or you might want to use the other, and that's the Chebyshev function. I've got the wrong code there. Chevy 1. Can't have that. Sorry. Oh, Chevy 1, long day. Chevy 1 RP. Okay. Nope. I'm ahead of myself now. Pause, go back. Everything's bad. Hi, I'm back and everything is awesome. Here's the code for the Chevy 1. It's almost exactly the same as the Butterworth. It's just got this one extra parameter in it. The Chevy trades off, it allows ripple in the passband so that you can have sharper skirts, shorter transition regions. So it's got this RP parameter, the allowable ripple in the passband, and you put that in, everything else is the same. So look at this filter or frequency response. See how there's a ripple here in the passband? That doesn't happen at all in Butterworth. This is Butterworth, totally flat. In Chevy, that there's a ripple in the passband, but then the transition region, that skirt, is much shorter. So passband ripple appears, passband gain is still 0, but now with ripple, there's a short transition region, and the stop band is still ridiculously low. Right, so also works. Basically just a different kind of distortion, but it cuts off high frequency noise more. So you'll probably have a higher SNR with Chebyshev because you've gotten rid of noise faster, like more aggressively, but you may distort your signal more because of that passband ripple. So here's the results from Chevy. It cuts off noise really sharply after 10K. Everything just goes to 0 right after 10K. We'll compare and contrast with the Butterworth. See how there's like a little bit of transition region with the Butterworth between 10 and 20K. The Chevy, it's all just locked off after 10K, just gone. Okay, and then, but then in the time domain, you can see this kind of wild, distorting oscillation. Is this good? Depends what's important to you. You certainly got rid of a lot of noise, but you did distort your pulse. Okay. All right, almost done. So the last thing here is let's look at that other example case where we had a bandpass signal, meaning we had a sinusoid, and we wanted a bandpass filter to remove all the frequencies away from 5 kilohertz. Okay, let's look at what that would be. So let's run through our 3 options here. If we use an FIR filter, we can do that to pick off the frequencies between 3 and 7 kilohertz in this case with a 50th order filter. Seems to work pretty well in the frequency domain. Everything goes to 0 away from 5 kilohertz. And then in the time domain, we see a pretty undistorted flat signal. Notice the sinusoid, though, doesn't come into focus. Like it's not accurate until after a little while, and that's because of the delay. All 50 delays have to be run through before the sinusoid is accurate. Okay, Butterworth. Mostly it's the same story. You cut off all the frequencies away from 5 kilohertz, you've got a sinusoid. Now you've got a little bit more distortion on your sinusoid. You can see the oscillation in amplitude is a little bit more extreme than in the FIR case, which is more flat. So more oscillation on your sinusoid. And then Chebyshev, we expect the least noise of all with Chebyshev, but more bouncing of our signal because of more distortion. All right, so in summary, we can use digital filters to improve SIR. I don't think there's any engineer in the world who's designing them by hand at this point. You just use the digital filter tools. FIR is good to know how to use. FIR is good to know how to use. Butterworth and Chevy will take out a ton of noise for you, but they will introduce distortion. So I kind of like to start with FIR and see if I can make that work because the distortion is less, but it's up to you. There's tons of options. It just depends on what trade-offs are important to you. All right, I hope this is helpful. Again, this is supposedly tying in discrete time systems and signal to noise ratio and giving you a new tool for your toolbox so that when you have signals and you want to improve the SNR and get rid of noise, you can use digital filters to do that. Okay, I'm posting these slides so you can refer back to them. Please go over this between now and Tuesday, and hopefully this will be something you can use maybe even on your second project. Okay, all right, thanks for your attention.